Hello students, the last time we solved a few questions about electric field due to multiple charges. Now we are going to study about an abstract concept which is related to the electric field. The name of the concept is electric field lines. I'm sure you've heard things like magnetic field lines of Earth, magnetic field lines of a magnet. Now, similarly, an electric field created by a charge, maybe positive, maybe negative, or a combination of charges, such an electric field can also be represented by using the idea of field lines. Now, I want you to understand a basic thing about field lines before we get started. It is just like on the Earth, we say that there's an equator, there's a line called equator. But the fact is, equator is imaginary. There is no real line drawn on the surface of Earth. Just like that, these electric field lines that we will draw to represent or to indicate the field, these field lines, they are imaginary, but they are a very good and a very simple way to show the properties of the electric field. Okay, right? So first of all, we're going to draw a vector field diagram. We have done it earlier. Okay, when I'll draw it, I'm sure you'll be able to recall it easily. So let's start. I'm going to draw a vector field diagram for a positive point charge. So if you remember, I told you that for a positive point charge, the electric field due to the positive charge, it radiates or is in a radial direction away from the charge, right, going outwards from the charge, right, and just like that over here as well. But I hope you remember that's not it. Over here we have electric field intensity with less magnitude. That's why a shorter arrow indicates the field at those points. Now, electric field lines is a related concept. It's that if you think about these arrows, and join them to make a curve, right? What do I mean? It's that instead of drawing separate vectors like this, which indicate electric field vectors, instead of that, if we draw a continuous line like I've drawn over here, so such a diagram is converted into this one. So obviously what we have drawn over here, this one, all these, they are all electric field lines, right? So this is the diagram of electric field lines due to a positive point charge, right? This is the diagram of electric field lines due to a positive point charge. As you can see, the field lines, I've indicated those field lines with arrows. These arrows, they are indicating the direction of electric field vectors. When you compare these diagrams, you'll understand that these arrows, they're referring or indicating the direction of electric field at various points, right? Now that's something very essential, it's very important. Okay, there's one more thing about electric field lines. Okay, if you would have a look at some if you have a look at some area over here, you could say there's only one field line. right? But uh, the number of field lines that we draw is actually upon us. It is arbitrary. We could draw 100 number of field lines between these two, okay, something in this manner, and obviously the same way in all these spaces, right? So how many field lines do we draw? That's a big question, and like I said, it is up to us. Okay, we could draw more number of field lines, we could draw less number of field lines, it's all up to us, right? So the idea is that if in some region the relative density of electric field lines is more, what do I mean? Think about, somehow, let's say that some charge in some manner has created this type of field lines. What we have over here is that the field lines are very close to each other in this region A, correct? But comparatively, in this region B, the field lines are a little bit spread out, they're a bit far away from each other, correct? Okay, so what I mean to say is that because the field lines over here are close to each other, right? Field lines are closer to each other comparatively, of, compared to that in B. So because of that, what we have is the electric field at B is in general weaker, has less magnitude compared to the electric field at A, right? Again, let me clarify what I've said. Electric field in the region B is weaker in magnitude compared to the electric field in the region A. Reason is the field lines at A, they are close to one another as compared to what they are in the region B, right? So what we need to understand overall about field lines is, number one, direction of electric field or electric field intensity at any point. Direction of direction of the electric field or electric field intensity at any point in space is indicated by tangent to the field line at that point. Okay, is indicated by the tangent at that point, right? And obviously this is supposed to be in direction parallel or in direction of the arrow. You should not forget this, right? Because a tangent is a line, right? I'll just stop over there. I'll come back to that topic later about what happens when we draw a tangent, right? Very shortly. The second thing that I have explained over here is that relative density, that is how close the field lines are. So maybe just to give you an easy word to remember, the closeness, right? The correct word is actually proximity, but that would be a bit tough for you. So relative density or closeness of field lines indicates the magnitude of electric field or electric field intensity again at that point or in that region. Okay, so these are the two important things that we have to keep in mind when we draw electric field lines. Let me just explain these two once again so that it is very clear in your mind what these points are. First one, again, have a look at this diagram. We start with over here, right? We put a test charge, test charge, test charge, test. We see that it will experience a force like that, and that's how we can draw the electric field vectors. So like I said, instead of drawing these separate electric field vectors, if we would just draw one curve, one line or one curve that would indicate or that would combine all of these. Okay, the information contained in all these vectors, it's combined in just one, right? So this field line indicates that the electric field at this point is towards right side, at this point is towards right side, at this point is again towards the right side because of the arrow. That's what this is indicating, right? Again, don't forget in direction of the arrow, right? So that's the first point. The second one is indicated or represented by that diagram. It's that suppose this is some arbitrary or random field line diagram. You could see that the field lines in this region A, they're close to one another, right? While on the other hand, over here at B, they're slightly far apart. So that means that the electric field at A has more magnitude compared to the electric field at B because the field lines are close to one another, right? So this is something that you must keep in mind when you draw electric field lines. Okay, right? Also, don't forget what I said over here is that the number of field lines is arbitrary. Let me just write that over here. Number of field lines is arbitrary. Arbitrary, that is, it's up to us how many you want to draw. Okay, right? You could draw more number of field lines, it's okay, no problem. But yes, it should be that if you draw some number of field lines and someone else has drawn some other number of field lines for the same thing, the two diagrams or two representations cannot be compared, right? Because the number of field lines actually indicates the strength, or the closeness indicates the strength or the magnitude of the electric field intensity, right? So be careful about that, right? So if someone will ask you how many field lines come out from a 1 coulomb positive charge, the answer is as many as you want, right? Okay, so don't forget that. Okay, so once we are done with these properties, they're not really properties, but the basic ideas about field lines, we're now going to discover some important points or characteristics of field lines, or maybe you could call them properties of field lines, right? So let's start with that. Right. So we are now going to talk about properties of electric field lines. Okay. Obviously, I've not written it here, but this definitely means we are talking about electric field lines right now. We are not talking about magnetic field lines or any other thing, right? Anyways, so what are electric field lines? What are the properties? First one, electric field lines start at a positive charge you could also write the word emerge. Emerge, that is come out. Okay, so electric field lines emerge or start at a positive charge and end at a negative charge. Okay, right? So electric field lines will come out or emerge from positive charge and they will only end at a negative charge, right? Okay. In other cases, electric field lines are continuous curves. Continuous curves. Okay. What is meaning of continuous curves? I'll tell you that in a moment. I'll explain both of these points by using diagrams. So in other cases, electric field lines are continuous curves that go up to infinity. Means that they don't end anywhere except for a negative charge, or they don't start from anywhere except for a positive charge, right? So these 2 points together indicates that when we draw the field line, we have to be careful that the field line always comes out from a positive charge. Okay, right? And if there's a negative charge, the field lines will go into the negative charge. Okay, so let's have a look at this diagram first of all. So there are many diagrams to be drawn. We'll draw diagrams as we write points. Okay, not like the first point refers to the first diagram. Okay, there's no link between them, but yet these diagrams illustrate or show what these properties mean. So here's one. So let's say there is a positive charge. So like I said, like I've written in the first point, electric field lines emerge out. They come out from a positive charge. In which direction? Well, in all directions, even in 3D, right? Field lines are also coming out like this, going behind the board. So this is one thing that the first one mentions. And you can see these are smooth curves that don't break. See, mathematically the word curves means any kind of sketch, any kind of diagrammatic representation. Okay, curves may also be a line, right? Is that clear? A circle is a curve, a parabola is a curve, hyperbola is a curve. Okay, a straight line is also a curve, right? So this is what is about lines emerging from a positive charge. Think about what happens at a negative charge. So this is a separate diagram. Please, do not get confused about these two being together. No, they are separate diagrams. Let me call it A, B, right? So in this case, we have a negative charge here. Again, before we draw the field lines, for a moment, I'm just going to draw the vector diagram. In fact, if you want to draw the diagram of field lines, many a times it's easy if you think or draw about the vector diagram for the field. Okay, so you could see that for a negative charge, the electric field vectors, they are towards the charge, right? Like this. So that means if I draw many of them, I'll be able to combine all of this and make a field line diagram that looks like, well, this. I don't think you have any problem understanding that, right? So not just 4, of course. Yeah. But again, the key thing to identify here is that because this is a negative charge, the field lines are coming in towards the charge and they are ending at the charge. I repeat, because we have a negative charge here, the field lines are coming in towards the charge and they are ending. Okay, they are terminating at the charge, right? At the negative charge, that is. So where are these field lines coming from? The answer is these field lines are coming from infinity. Read the second one. It says that otherwise, in other cases, that is, what this means is, here we have a negative charge, all right. Okay, so field lines will end over there, but where will they come from? Well, because in this diagram there is no positive charge, we don't know where these field lines are starting at, right? We don't know where these field lines are starting at. Okay, so that means that these field lines, they have come all the way from infinity, and from infinity they've come to this point, to the charge, and they have ended over there, right? Just like that, where are these field lines going? Well, they are going to infinity because we have just put one positive charge in space. There is no other negative charge. Remember, these figures are different, right? They are different cases, right? So what happens is that the field lines come out from this positive charge and they don't end anywhere, right? They don't end anywhere because there's no negative charge, so they just go out in all directions up to infinity. All right, so that's what we have for these two figures, right? Remember, the properties of field lines is one of the important theoretical questions from this chapter. I would expect you to remember these properties of field lines, and along with that, be able to draw these diagrams. Trust me, that's all very simple. Okay, you just have to understand the basic idea behind it and draw it roughly, and you're done. Okay, so number 3 now. Electric field lines do not intersect each other. So what does that mean? Have a look at these. What we have is that the field line number 1 starts from this point charge over here. Don't forget, this is just a point, and it goes out. The field line number 2, it goes out over here. You could also write that they do not cross each other. Okay, they don't intersect or don't cross each other. So why is that so? The reason is, think for a moment that suppose the field lines in some case are like this, that they're crossing each other at this point P. Let's call this point P. Okay, so they're crossing each other at P, right? Now an interesting thing would happen at P. If you'd recall the basic ideas behind a field line, electric field line, it is that if we draw tangent at P, we're going to end up in a very strange situation. I could draw the tangent in this direction, possible, or I could draw it in this direction, right? That is either here, again following the arrow, or here, right? Okay, excuse the bad drawing, over here. Then the question will be, the electric field at P is in which direction? Is in which direction? Is this the one that's correct, or is it the one that's correct? So the problem is, one vector cannot be in two directions at the same place, at the same moment, right? It's like, suppose there's a vehicle moving, then its velocity at a particular point, at a particular time cannot be in two different directions. It's either this way or that way. It can't be both, right? So the same problem over here, right? Think about wind direction. At one particular place, at one particular time, the wind direction cannot be two separate. It's not possible that wind is blowing north and wind is also blowing west. Okay, so just like that, if these two field lines will cross each other, we're going to have a problem. We're going to have this problem, right? So that means the electric field lines must not or can never cross each other, right? Again, I'd like you to recall that electric field lines is an imaginary concept. There are no lines drawn like this anywhere by nature, okay, right? But like I've said, it's a very useful idea. Just like thinking about equator on Earth is a very useful idea. Same thing, when we start describing and using the ideas of field lines, understanding how electric field and charges behave becomes very simple. Okay, so don't forget the third point. It's one of the most important things. Electric field lines can never cross each other, because if they did, we'd have the electric field at that point in two different directions. That's not possible. It has to be in one direction. That's why it can't cross. Okay, right? Next, electric field lines of a uniform electric field lines of a uniform electric field are parallel and equidistant to each other. What does that mean now? Okay, what does that mean? First of all, let's attack this word. Equidistant means at equal distance from each other, and I'm sure you know what is parallel. So let me draw a diagram that represents what we have here. Okay, so suppose that this is a uniform electric field. Okay, let's say we're drawing a diagram for uniform electric field. Then this is what it would look like. Again, I'm trying my best to make these parallel to each other and also equidistant. That is, this spacing, whatever that is, would be the same. Okay, right? Is that clear? Right? So what we have is that the electric field lines, they are all at equal distance from each other, and they're all parallel. That is, they're in the same direction. Now, why do you think it should be like that? Why? Why is it that uniform field cannot have, possible electric field line diagram like this? Think about it. Why not this? Why is it like this one? The reason, you'll understand the reason if we'll think about the basic ideas, the two things I told you about at start about field lines. One, the direction of the arrow, the direction of the electric field and the direction of this arrow is the same. So you can see for a uniform field, it's necessary that the field direction is same at each point. So obviously, if the field lines would be in this manner, then the field direction here at the point A and the field direction here at the point B, they're not same, right? This one's over there, this one's over there, so doesn't work. That's not uniform. Not only that, if it was like this, like a good, that diagram, this diagram does look like this one, correct? So I want you to notice something. Like I mentioned earlier, over here in this region, these field lines are close to each other. But over here, they are not. They're a bit far from each other, aren't they? So that means in this region, the field is strong. The magnitude of the electric field is more. But in this region, the magnitude of the electric field is less. Correct? But such a field cannot be called uniform, right? If you recall the second point again, it is that the closeness of the field lines indicates the magnitude of electric field. So you could see they are equally close over here as they are over here because they are parallel, right? Okay, so you could see the property for uniform electric field to have parallel and equidistant field lines is necessary. That is how it should be, right? Okay, so that's the diagram for a uniform electric field, right? So now I want all of you to really be able to draw such diagrams on your own, right? It's actually very simple. Okay, right, fine. So that is what a uniform electric field looks like, right? Now there is one last property of electric field lines that I must tell you. Number of field lines crossing a unit area perpendicular or normal to the field lines indicates the magnitude of electric field intensity, again the magnitude of the electric field intensity at that point. Okay, this one is very closely related to the second idea about drawing a field line. It says that if the field lines are close to each other, the field is strong, has more magnitude. But if the field lines have distance between them, they are a bit far apart, then the electric field is weak or has less magnitude. So let's try this sentence over here. Suppose I draw some unit area perpendicular to these field lines. Okay, let's say that's a unit area. 3 field lines are passing. All right, now let me draw it here, or let me draw it here. You're going to notice that we have the same number of field lines passing through that. But if I try something like that over here in this diagram, let me just draw it again. Okay, right, so okay, so if I draw some unit area which is perpendicular or normal to the field line like this, so let's say it's passing through 4 of these field lines. Okay, the perpendicular area is curved because it has to be, like I said, perpendicular, right? Okay, it's like light rays coming out from a point. and this area is covering it like this. Okay, think about the same area, think about the same unit area drawn over here. That is what it would be like. But you could see now clearly that if you talk about the unit area 1, more number of field lines pass through unit area 1 compared to unit area 2, right? You can see that here about 4 lines are passing, over here only 2. So that's because as you go away from a positive point charge, the magnitude of electric field will decrease. Let me repeat what I've said. 4 field lines passing through this, 2 field lines passing through this. Okay, that's because over here, close to the point charge, the magnitude of electric field is more compared to this far. That's because of the fact, due to a point charge, the magnitude of electric field is given by E is equal to kq by r square. So if distance will increase, the magnitude of the electric field will decrease. Okay, so keep all this in mind, right? So that's the property number 5. Obviously the same thing applies over here as well, but it's okay, there's no need to show it for each of the diagrams. Okay, so these are the 5 properties of electric field lines. Let's quickly go through all of them. First one is that the field lines start at positive charge and end at a negative charge, right? The second one is where there are no charges, the field lines will go to infinity and they are continuous curves, right? Field lines are continuous curves that go up to infinity. So you don't know where they might end or where they might start. But again, continuous means without breaks. Okay, it will not break except when it's at a positive charge or a negative charge. Third one is that 2 field lines can never cross each other, because if they did, we'll have this problem, right? At that point you'll have 2 tangents, and that means you'll have 2 directions of electric field at one point, which is impossible. Okay, the next one, number 4, is that if you have got a uniform electric field, then the field lines of uniform electric field, they're all parallel to each other and they are equidistant from each other. And finally, number 5 is that if you draw a unit area perpendicular to these field lines, okay, then the number of field lines that pass through that area indicates the magnitude of electric field. Okay, so those are the 5 properties of electric field lines. Now for practicing this, I am going to assist you, I'm going to show you how to draw the electric field lines for a system of 2 charges, right? One positive and the other negative, right? So far, if you realize over here, we have drawn it only for individual charges, single charges, right? Now we are going to draw it for a system of 2 charges. Let's see. So let's say that here we have a positive point charge and here we have a negative point charge. Okay, so what we're going to do is we have to use all the properties that we have learned. We have to use the basic ideas about field lines as well. So let's start. Property number 1 says that the field lines will start at a positive charge and end at negative charge. Okay, so what I could do is I could think of some line that starts from here and ends over there, right? But that's not it. You have to be slightly careful when you do that, because it's possible that all field lines don't end at the negative charge, right? They might not all end at the negative charge. What do I mean? Let's have a look. Suppose we're going to detail this completely. Suppose you think of this point, which is exactly the midpoint of these two charges, right? So at this point, due to the positive charge, let me call it charge 1 and charge 2. Due to charge 1, the electric field is on the right hand side. Due to charge 2, again it's on the right hand side, so the net field is in this direction. Same thing for this point, same thing over here. So one thing is clear, the electric field line will be from the positive charge to the negative charge. That's one of the lines. But if you think of a point over here, let's say the positive charge will have electric field going away from it, but the negative charge has a electric field going towards it, towards the source charge, right? But the fact is, you can't have electric field in both these directions simultaneously. So what happens is, due to two charges, there is a resultant of the electric field. That's superposition principle, and we will have the net electric field somewhere in this direction by using the law of parallelogram, right? Don't forget the fact that although I've indicated this direction, if I draw it vector notation properly, this arrow is going to be short because this point is far from the charge 2. So the magnitude is less, but for the first charge, the electric field is stronger because this is close. So that's why this is what it will look like. Just like that, if I go to a point over here, symmetrically located over there on that side, you're going to see the same thing happens, but due to charge 2, it's going to be over here, and due to charge 1, it's going to be over here, right? Okay, so the net of these two, net electric field of these two, would be somewhere along this line. So what happens is, I can actually create a multiple which indicate the electric field directions at various points, right? You could verify that over here at the center, exactly on the midpoint of these two charges. What we have here is that at this point, the electric field due to positive charge is in that direction, but electric field due to negative charge is in this direction, but these two are symmetric because of the fact that this is exactly on the perpendicular bisector. That's why the net field is towards the right hand side. So what happens is, when I'll join all these arrows together, what we get is a smooth curve from here to here. We get a smooth curve from here to here, and that is what becomes our electric field line passing through this point, right? So let me just erase all the other things, all the other elements of the diagrams that we use. So finally, we have got this field line. Now, I did this for this point, but that's not necessary. I could have done it for this one as well. In that case, we get it like this, going from the positive charge to the negative charge, or maybe like this, okay, or like this, correct? So this is how you're going to have field lines going from the positive charge to the negative charge. That's not it. We have field lines going from here as well, right? Okay. So I'm sure you have understood what we are doing. But it's also possible that these field lines which are going from positive to negative, there are some field lines that will actually go off very, very far. I hope you realize what I'm trying to suggest. Okay, there will be field lines everywhere over here, but these field lines, they are going to go very, very far, and obviously when they'll come back, this is what it would look like at the negative charge. So obviously you can't go everywhere in the universe to draw these field lines, because they can go up to infinity, right? But this is what the diagram of electric field lines looks for a system of a positive charge and a negative charge. Okay, see, it does follow, or does have to follow, all the properties that we have talked about. First one, lines will start at a positive charge and end at negative charge, right? And in space or in places where there is no charge, they will be continuous. They will not break. Obviously, like I've said, these lines, they don't really start from here. They go till infinity, but unfortunately, I can't draw it till that point. Okay, so they don't really start over here or end over here. So that is how this works, and it's that all these lines, they don't intersect each other. They don't intersect each other, as you can see, because if they did intersect, what that would mean is at one point the electric field will be in two different directions. That is not true. Okay. One more thing that I want all of you to notice is, you see, look at this part. The electric field lines are so close to each other. Same thing over here. That's because when the point, all these points, they're very close to the charge. Close to the charge, the magnitude of the electric field is really very, very high. But if you compare that with, this region, you see there the magnitude of electric field is not that large because it's a bit far from the charge, right? So you see that over here the field lines are far apart. They're not very close to one another, right? As you come close to these charges, either here or there, either positive or the negative, as you come close to the charge, the closeness, the density of electric field lines is increasing. That's the key point, right? Okay, so that's what the electric field diagram or field lines diagram of a system of positive and a negative charge looks like. The last property of electric field lines is that electric field lines, rather electrostatic field lines, do not form loops. Okay, what does that mean? It means it cannot be something like this. Repeat, it cannot be something like this. This is not allowed. Okay, does not form loops. Okay, so this is something which electrostatic field lines cannot do, right? So remember, any kind of a closed curve that comes back to itself is a loop. That is not allowed for electrostatic field lines. You would have noted that so far I was just saying electric field lines and not electrostatic. The reason why I'm saying electrostatic here is that this refers to charges that remain stationary. Electrostatic is referring to charges that remain stationary. Well, the fact is that the rest of the properties that we have studied, they are valid for charges which are stationary, that is electrostatic, and they're also valid for charges that are moving. Okay, so but over here, this last one, this is only true as far as charges are stationary, right? So this is the property of electric fields created by charges that are not moving. Okay, so remember that if we are talking about electrostatic field lines, they can't form a closed loop. Okay, so that's it for the properties. Okay, and now after having finished properties of electric field lines, we are now going to study about electric dipole. So what is an electric dipole? Let me write a definition first. It is a system of two point charges of equal magnitude but different polarity and separated by a finite distance. Okay, so you don't need to worry too much about how we get this definition. It's very easy to write the definition if you have the diagram in your mind. Let's see. It says that we have a system, a collection of 2-point charges. Let's say one over here and somewhere else the second one. Both of equal magnitude, different polarity, and separated by some distance. So let's say one positive charge Q1 here, okay, whose magnitude is Q, and another charge Q2 over here, but its magnitude is Q again, but the polarity is negative. Okay, so one is Q, the other is minus Q. Okay, you could also indicate it like this if you want. Okay, positive charge and a negative charge. Don't forget these are point charges and they are separated by some distance. Now conventionally we tend to write this distance as 2a. We write the distance between these two as 2a, that is double of a. So obviously that would mean if we take the midpoint and divide this distance into 2, so you have a each. So from the center of the dipole, C for center of the dipole, so from the center of the dipole the distance of each charge is a, so the total distance being 2, right? So this is what a dipole looks like. Again, 2-point charges, they have equal magnitude but they have different polarity and they are separated by some fixed finite distance, okay, 2a. So this is what is an electric dipole, right? Now we're going to talk about one more definition, which is regarding a property or a characteristic of electric dipole, and that characteristic is called electric dipole moment. Okay, it is called electric dipole moment. Now I'd like all of you to recall the word moment. For example, moment of linear momentum or moment of force. Can you recall these things? The moment of force means torque, which is more or less like some perpendicular distance multiplied with the force, right? Same thing here. An electric dipole moment is, roughly speaking, some quantity multiplied by a distance. So what exactly is it? Let's see. It is the product of magnitude of charge and the separation or the distance between the charges of dipole. Okay, so it is the product, the multiplication of magnitude of charge and the distance between the charges. The symbol of electric dipole moment is P. Right now I am putting it in a scalar form. It is a vector. Okay, electric dipole moment is actually a vector. Its magnitude is given by, read this, you should be able to write its equation. It is equal to 2a into q. Distance between the two charges, 2a into q, that is the magnitude of charge. Again, this is q and this distance is 2a, and that's why it is P is equal to 2aq, right? That is in scale, that is the scalar, the magnitude of the electric dipole moment. Now if we want to talk about a vector, okay, so I'm going to write a sentence that tells you about its direction. It is the direction of electric dipole moment is from the negative charge towards the positive charge. Okay, is from the negative charge towards the positive charge. So if I want to indicate the dipole moment in a diagram like this, let me just draw a separate one here. Say this is positive and this is negative charge. Then the electric dipole moment is a vector in this direction from the negative towards the positive. Again, this is only an indication of the direction. Okay, from the negative towards the positive. You could write here or here, doesn't matter really. But don't think that its magnitude is equal to 2a. No, the magnitude of this vector is equal to 2a into q. That is, it's the product of the charge of the dipole multiplied with the separation, the distance between the two charges. Okay, so that's what is an electric dipole and its electric dipole moment, right? You might wonder, what's the need to define such a thing? The reason, the need is that this kind of term, the electric dipole moment, appears often when we try to find out about the electric field due to such a system of dipoles, right? The fact is, atoms, they are a very short, a very small dipole because of the fact that positive charge is in the nucleus. Okay, right? But the electrons, they are at some distance from it, correct? So due to that fact, every atom does behave like a dipole, and so do molecules. I'm sure you have studied that in chemistry as well, that there are several kinds of molecules that have a dipole moment, and then there are some others that don't, right? For example, water molecule has a dipole moment. So these things do play important role in the electric field created by these charges, right? So that's why we are defining something like a dipole moment. Okay, so now to practice this idea, I would like all of you to solve the question number. Let me just write it over here. Please solve the question number 1.9 from the exercise. Okay, I want you to solve the question number 1.9 from the exercise, right? That will make you ready for finding the dipole moment. It's about dipole moment. Be careful though, students tend to make a mistake. It's that if someone says that the distance between these two charges is, let's say, 1 centimeter, if the distance between these two charges is 1 centimeter, then the value of A is not 1 centimeter, the value of 2A would be 1 centimeter. I hope you have got what I'm saying. It's a very common mistake. So ultimately, when you try to find this whole bracket 2A itself is 1 centimeter. Okay, so be careful about this idea, right? I thought I'd just warn you before you solve that question. All right, so I really think that's it for this class, right? The next time we are going to solve, we're going to find out and solve questions related to the electric field created by such a system, such a dipole, right? Okay, so you're going to find that what we'll do the next time in the next class is going to be useful to find out the magnetic field due to earth or due to little bar magnets and all that. Okay, so what we're going to do next time has big implications for you. Please make sure you solve that question before you watch the next lecture. All right, goodbye.